So the key point that I'm trying to make here is that all the threads in a var will still proceed in lockstep. It's not the case that lockstep execution will not happen. It is just that for every instruction, a thread needs to assess whether the instruction is in its correct path or not, right? If it is on the correct path, then what it will do is that it will basically process the instruction, compute the results, and update the state. Otherwise, it will ignore it. All right. And for more of predicated execution, you can go to the chapter on Itanium, chapter 5, the lecture on Itanium, the last lecture of chapter 5. So let's look at predicated execution, the previous example. Assume there is thread 1 and thread 2. So both will execute the if statement because here they are evaluating whether x is greater than 0 or not. So of course, x is a thread specific variable here. That is why this instruction falls in the correct path of both threads 1 and 2. Now, if we look at the body of the if statement, then the body of the if statement is in the correct path of thread 1, but for thread 2, it is on the wrong path. So thread 1 will process the instructions and thread 2 will just ignore. Finally, the body of the else, well, for thread 1 will not process, thread 2 will process. And this is known as the point of reconvergence, because this is when thread 1 and thread 2 start processing. Both of them start processing the instruction. So you can say that this is where the if statement kind of ends. So this is the point of reconvergence. So how is predicated execution achieved? Well, each thread maintains a stack. When we enter the body of an if or else statement, what we do is we push our 1 or 0 onto the stack, depending on whether we are on the correct path or the wrong path, respectively, right? So let's say I'm entering the body of an if statement or an else. What I do is that I push a value onto the stack. So I'll come to a second why it's a stack. So if, let's say I'm on the correct path, I push a 1, otherwise it's a 0. Now coming to the fact why it's a stack, well, because we could have nested if statements, right? So if that is the case, it is very well possible that I may be on the wrong path of the first if statement. And after that, I come and then, maybe I do a comparison and I see that I'm on the correct path of a if statement that is nested in the outer if statement. But this doesn't matter because I would have not entered this piece of code anyway, right? So what I basically do, right, or what is supposed to be done is that the stack maintains the fact, if you see there is a last in first out behavior. The last in first out behavior comes because if I have one if statement, I have one more, I have one more and so on, then I enter this if statement's body at the end and I also exit it the first. So it's last in and first out. Again last in and first out. Again last in and first out. So the moment we have a last in first out behavior, we use the stack data structure. The stack data structure is basically used to store the outcomes of the branches or whether I'm on the correct path or on the wrong path. So to ensure that I execute an instruction, all the entries in the stack, assuming that even if I'm on the wrong path of an if statement, at least I do the comparison, right? All the entries of the stack have to be 1. Then only I can say that a given instruction is on the correct path, it should be executed, its result should be computed and committed to permanent state. Otherwise, if any one of these entries is 0, then I will say that I am on the wrong path. Okay? And the instruction should not be executed. So there are two conditions over here. The first is that the instruction is executed if the stack is empty. Yes, that's obvious. Or as I have just described, right, that the last in first out stack, if all the entries in the stack are 1, so this is, so we have a separate stack for each thread. This is not the programming stack, okay? It's a separate stack which only stores the results of predicated execution. So if all the entries in this predicated stack are 1, so we have 1 stack per thread, 1 per thread. Okay. So we maintain 1 stack per thread in the var. So if all the entries are 1, then the instruction is on the correct path and it is executed. So when we leave the body of the if or else statement, we pop the stack. All right. So this is what is done, that we push an entry when we enter the if statement, and when we leave it, we pop an entry of the stack. So who adds all of these codes? Well, all of this code is added by the CUDA runtime in terms of special instructions or directives or bits that are sent to the hardware. And the hardware then picks up these queues and maintains the stack for the thread. So the stack is maintained in hardware, but of course the directives of when to push and pop are given by software. Let us now look at a slightly longer example with 3 threads. So in this case, we have nested if statements. So the first if statement is executed by all 3 threads, as you can see over here. Then we have our first if statement. So the first if statement is executed only by the first 2 threads and not by the third one, which is thread 2. The reason being that this predicate for thread 2 is false. X is less than 0 for thread 2. Then we execute the body of this if statement. So as you can see, the body of the if statement for thread 1, both the predicate bits are 1 and 1, which essentially indicate that it is on the correct path of thread 1A. But for thread 1B, even though it passed the first if statement, it was not able to pass the second if statement. So that is why for thread 1B, this predicate here is false. So that's the reason instead of pushing a 1 onto the stack, we push a 0. And because we have 1 0-valued entry, this instruction is on the wrong path of thread 1B. And that is why this instruction is not going to be executed, it will be ignored. Similarly, since we are already on the wrong path, as I said, we may decide to do a comparison, we may decide to omit it. In this case, we don't do a comparison for thread 2 because we are on the wrong path anyway. So we again push a 0 onto the stack. And so for thread 2 also, this instruction is not executed. At this point, threads 1A and 1B reconverge. So we pop the stack. So this entry is popped for all 3. So you're left with 1, 1 and 0. So again for thread 2, this instruction is not executed, whereas for threads 1A and 1B, this instruction is executed. Finally, we have 2 instructions over here for thread 1A and 1B. The else path for both of them, right, is they are on the wrong path. So how did we arrive from this state to this state? Well, the moment we exited the if statement's body, we popped the stack, it became empty. And then we pushed 0 onto the stack because we are on the else path for thread 1A and 1B. So it's a wrong path. So we push 0 and 0. So clearly for these 2 instructions, thread 1A and 1B will ignore them. But for thread 2, the else path is the correct path. And that's the reason we pushed 1 onto the stack. So thread 2 will execute them. So as you can see, in every stage, instructions are executing in lockstep, right? So basically the same instruction. Instructions are executing quite well, in fact, in lockstep. And now, for the last instruction, which is x equal to c, this is where all the threads reconvert. So it's called the POR, or the point of reconvergence. So at this point, all the threads, which are threads 1A, 1B, and 2, they reconverge. So then what happens is that we execute the same instruction for all 3 threads. So this is a good idea in the sense that using warps has made the operations of GPUs extremely efficient. However, such lockstep execution has its share of problems, and we will see why. So assume that we have code like this, okay? So if we have code like this, let's assume that we take an internal variable x, okay, and we initialize it to 0. So this is a per thread variable. No, I'm sorry. This is a shared variable, and it's not a per thread variable, it's a shared variable. It's initialized to x. Then assume that we have 4 threads, 0, 1, 2, and 3. So for the 4 threads, let's say for the first 2 threads, you will find that thread idx.x is less than 2. Why? Because it is 0 and 1. Okay? So this x and this x are different. So this is the x coordinate of the thread index, and this is a shared variable. So they are different. So for thread 0 and 1, they will enter this if statement. And because they are entering, the other 2 threads, threads 2 and 3 will also enter. Because we execute this instruction, where the same instruction in the warp is executed by all the threads. Of course, for the threads 2 and 3, this instruction is on the wrong path, but they will wait for their sister threads 0 and 1 to complete this. So here the fun begins. If we have a while loop over here, which waits until x is 0, we'll be stuck forever. The reason we'll be stuck forever is basically because there is nobody who's going to set x to a value which is not 0. But if you look at this logic, so by this logic, threads 2 and 3 should be executing these 2 instructions, which of course are on the wrong path of 0 and 1, but for 2 and 3, they are on the correct path. On the correct path, they will set x equal to 1, and this is going to release the while loop over here. But the point is that we will never come here. Okay? And so basically the point is that we are never ever going to come here. And the reason is that the other 2 threads which are supposed to set x to 1 and release it, they will not come here because they'll keep waiting for their sister threads which are 0 and 1 to exit, right? And they are never going to exit the while loop. So we'll be stuck forever, even though we should not be. So of course, we are not assuming 2 threads over here. We are assuming 4 threads. So the point is that if you look at the simple logic, as such, there is no problem. But when you take a deeper look, you will realize that we are never going to reach this statement only because of our constraints on lockstep execution within a warp. So this is of course a slightly contrived example, but we will find many more such situations in real life where such interactions do happen, and many times the code goes into a deadlock and the developer has no clue why. So that's the reason in modern GPU design, such situations have been avoided. To precisely avoid such situations, which may arise inadvertently in an execution, there is a notion of limited yet controlled thread divergence. So let us consider the 2 code blocks. So let this be the while loop. Let's call it W. And the other code block, let's just call it X for the one that's setting X equal to 1 and Y. So what we can do is that we will not stop our basic lockstep execution paradigm. We will go with what is called restricted lockstep execution. We'll execute the while loop for some time, which is the first point. We execute the while loop for some time. We see that we are not making progress, right? So this can be seen that, the while loop is just going on and on. So of course, we can't detect an infinite loop, but at least we will see that we are there in one region of code for some time. We can then go to the else part and again execute it for some time. This again will follow the lockstep paradigm. So all the threads will again execute the else part. Of course, all the predicate relations will be preserved. So only for all the threads whose predicates are all 1 in the stack, they will execute, others will not. We have seen that. So the X and Y blocks will be executed. The advantage of doing this over here is that X equal to 1 will be set by some thread. Doesn't matter who. Finally, we can come back to the while loop, and the two threads which should have executed instructions in the while loop, they will execute it. And basically, the others will ignore, but at least they will exit the while loop. So since the if part and the else part, all the threads have exited both, we can enter the point of reconvergence over here. So what you are basically seeing is that we are again coming back to the while loop after executing the else part. So this was the if part, this was the else part, and this was the if part for the second time. So we're again coming back to the if part. So this is an example of restricted lockstep executions where we are not really letting the threads diverge or go their own way. Right, so the threads are still executing together, they are still in lockstep mode. So we are referring to this as the restricted lockstep execution. Where, as you can see, there's this if else if kind of jump. So this allows for reconvergence, as we have seen. And the deadlock situation that was arising here in the previous thread, in the previous example, I'm sorry, this is not arising over here. Right, so this is one of the big inventions that happened in NVIDIA Volta and has subsequently been kept. And because this was required, otherwise there were many of these sticky kind of race conditions which were happening primarily because of our insistence, dogged insistence on lockstep execution. So now we're in a position to see the GPGPU pipeline kind of in full glory. So this is, let's say, the pipeline of a PB. So we have a fetch logic and an instruction cache which uses both the I0 and I1 levels. Then we have a decode. So then the rest of the, the scheduling part, the warp scheduling has, so the decode could be part of the fetch, could be part of the warp scheduler, doesn't matter. But the key aspect of the warp scheduler over here is that it uses a scoreboard. So we have seen a scoreboard earlier, so that's the reason I'm not explaining it once again. We have seen it when we were discussing Atanium, which was the last part of chapter 5. So if you go to the video, the last part of chapter 5, you will find the videos on Itanium. And the videos on Itanium have a discussion on the scoreboard. The scoreboard is nothing but a hardware data structure that keeps an instruction stalled until there are no hazards. But the hazards are of 4 types. And structural hazards. Until these 4 hazards, there is no probability of any correctness problem happening because of these hazards. We just stall an instruction. After that, we issue. So since the scoreboard has been discussed in detail, I'm skipping that part, but this was discussed in detail in Itanium. And finally, we have the register file access. As you have seen, the register file looks like a memory in a PB. And then we have a bunch of these functional units, which could be the integer ALU, floating point, single precision, double precision ALU, special function unit for sine, cos, transcendental functions, load store units. Load store units talk to the L1 cache, the shared L1 cache, and finally to the DRAM. Right, so I forgot to add an L2 cache over here. There should have been there. But still, the GPU DRAM has a very large role to play in the GPU because a lot of the data, because we're dealing with big data over here, a lot of the data ultimately ends up getting stored in the DRAM. And for regular functional units, once the operands have been calculated, there's a register write back, and we again write the results back to the register file. So this is as such a regular pipeline. The scoreboard is new, but the rest are not that new. The scoreboard basically tracks the dependencies and stalls instructions until the dependency is met. And it's an in-order pipeline. It's not an out-of-order pipeline. It's primarily an in-order pipeline to a large extent. But of course, you will see in an in-order pipeline, wow and war hazards don't come up. So basically there is a very small amount of outer orderness over here, and which is sometimes, if you have this kind of execution as I just showed on the previous slide, there is a limited amount of that, but in general it's the job of the scoreboard to take care of these issues, right? Particularly when we are executing threads in this fashion, is a job of primarily the scoreboard to take care of it. So the important question that needs to be answered now is that if, let's say, we have 32 load instructions in a word, or 32 store instructions, pretty much one instruction per thread, what do we do? How do we access it? So let us first count the number of bits that we need to read at the same time. So of course, same time may not mean the same cycle, but let's say in the window of 2 or 3 cycles. So it's 32 cross 32. Well, why? Because we have 32 threads in a word, and each value is 32 bits. So this is 1024 bits or 128 bytes. So this would require a very high register read bandwidth and a very high register write bandwidth as well. So if I were to argue in a different way, so you may say that, look, instead of sending 32 requests per cycle, we may send 16 or we may send 8. Well, that's fine. So if we send 16, you should also factor in the fact that if, let's say, an instruction has 2 operands, we are not reading 1 operand, we're actually reading 2. So this will become 16 times 2, 32. Again, multiplied with 32, it will remain 1024 bits, right? And let's say if we send 8, well, then it will become 512. But that's still a lot of bits. A simple yet impractical solution could be that we just have a register file bank. A bank is nothing but like a sub-register file. And then each entry could be 1024 bits where all the entries are kept together, where all the information is kept together. This is impractical. Okay, this simple idea is impractical because we don't know in advance which registers we'll access and whether they'll all be kept at the same place or not. So this is rather impractical and doesn't work that way. And also reading out so much of data takes a lot of time. A far more efficient solution is to actually split the register file into multiple banks, sub-register files, and distribute these 1024 bits across these register file banks. So one bank can keep, let's say 64 bits or 128 bits. If, let's say, it keeps 128 bits, then across 8 banks, the data will be distributed. So we'll need to have an elaborate network. So that is what the crossbar network is, which is controlled by an arbiter circuit. To access all those banks which have the data, read them or write them. So let's look at read because read is more performance sensitive. And we put all of that data in a dedicated hardware structure called an operand collector. So the job of the operand collector over here is to basically work like a temporary buffer till the data is completely read from the register file banks. So clearly we're accessing multiple banks. So from each bank, we're reading a lesser amount of data. So what is happening is that this is a fast access and also there is parallelism. We have exported the complexity to the network. That's the reason we need an intelligent arbiter. But once that is done, all the 1024 bits can be read and they can be stored in the operand collector. And from the operand collector, the data can then seamlessly pass through to the execution units. And the execution units can then execute on the data, execute the function, whatever it is, add, subtract, multiply on the data. So the key innovations over here are the crossbar network, the arbiter, and the operand collectors. So as we have discussed, a simple yet impractical solution is to just make a register file bank entry wide, 1024 or 120 bits wide. That's not practical. You have to have a large number of banks in a register file, use the operand collectors to collect the values, and then use the on-chip network to route register file values to the operand collector as we have seen. Even in the L1 cache, when you're accessing the caches, not L2 to that extent, but L1 definitely, there's a far elevated chance of bank conflicts. The reason is if you're writing data, we are writing 128 bytes, or it's maybe easier to say 32 memory words, where a word is 4 bytes. So clearly, if we are accessing multiple banks, there is a chance of bank conflicts in the sense that a single bank may contain 2 of these words. So if you have concurrent accesses to the same bank, that's a problem. So what we can do is we can have a dedicated piece of hardware that will send all the mutually non-conflicting accesses to the banks first. So out of, let's say, all the accesses, let's say 32, we might find 25 accesses that are mutually non-conflicting. We send them first. Then in the rest of the accesses are sent to subsequent cycles, are sent to the banks in subsequent cycles. So they're gradually drained off. For writes, what we can do is that, let's say if there is a cache line, then what will happen is the data will gradually come in because of bank conflicts and so on. So whenever we bring in a line from a lower level, we can lock the line in the cache. And let's say we'll have an MSHR kind of structure. So we'll discuss that in great detail in chapter 7. But what we can do is that, let's say, I'll give a realistic scenario. So let's say that in the L1 cache, there is a write miss. So the clock has to come from L2. In the time being, a lot of reads and writes would have arrived at the L1 cache. So they're buffered in a temporary structure. That will be called an MSHR in the next chapter. But in this chapter, let's call it a temporary structure. So the temporary structure will hold on to all of the outstanding reads and writes. And the moment that the block comes from the lower level, we'll basically replay all the load store accesses for the set of all the lines that arrived in the shadow of the miss, which means when the miss was being serviced from the lower level, whatever reads and writes we got, we immediately apply them to this block over here. So now we have reached the end of the chapter. So let me quickly conclude. We always have 5 concluding points. GPUs are no doubt a vital requirement in modern numerical, scientific, and high-performance computing. They are required for accelerating graphics-based applications, no doubt. CPUs, in comparison, have severely inadequate resources. Early stage GPUs were too customized for specific applications. But then GPUs arrived on the scene and they had a very generic application. The CUDA language was developed to basically run generic codes on GPUs. A CUDA binary is a fat binary that has both GPU and GPU specific code, CPU and GPU specific code. And GPUs have a complex hierarchical structure with 5 to 10,000 cores these days, which is massive, right? Several teraflops of computational power is there within one single GPU. So here we have a GPC, then a TPC, SMPB, and a bunch of variables. A WAP requires 1024 bits in one go. This necessitates a complex and a multi-banked register file and a complex multi-banked L1 cache as well. So we will discuss in the next chapter on caches a lot more about the way that these caches are designed, because what you would have realized by this time, which is at this time meaning that we have completed the first part of the book, where we have discussed out-of-order pipelines and GPUs, and it is possible to embed a sea of computational units and increase the IPC for some codes, not for all. But the memory system can be a bottleneck, because the memory system also needs to provide data at a high rate and also read out results at a high rate. Correct? The memory system could be a bottleneck. Given the fact that the memory system is a bottleneck, or can be one, we should invest a lot of our resources in designing a very fast and efficient memory system. So this will be the subject of study in the second part of the book, which is from chapters 7 to 10, and the lectures for this you will find on the website for chapters 7 to 10. So kindly follow.